So today we are going to just look at the tutorial for the backtracking algorithm, and it's going to be fun. I think I'll start with this cool article that I found on Geek for Geeks. I don't know who wrote this. Probably I am not going to find it because this is the first time that I am actually using it. Where no, I couldn't find it. Okay, let's go through what is backtracking. So I have a basic idea of backtracking algorithms, but I just need to like have a proper idea. So I just thought to look at this and have my thoughts on that. So algorithm tutorial. Okay, backtracking is like trying different paths, and when you hit a dead end, you backtrack to the last choice and try a different route. So what do you mean by that is so basically I've created this maze to just it's not a good maze, but oh, that's all that I can do. That's all that I can do. So you go this way, you hit a dead end, and you come backtrack to this previous point where you could have taken a different way. That's basically what they are trying to say. So yeah, I was saying, in this article we'll explore the basics of backtracking, how it works, and how it can help solve all sorts of challenging problem. It's like a method for finding the right way through complex choices. Okay, choices, complex choices. Okay, that's what I'm thinking about. Like the choice should be complex. It's what they mean by complex is pretty much of you have various choices, and the it's not easy to come out of the choices. Probably they mean by that's why they mean by complex. uh, oh, it could be they could have just gone with the word like what do you mean, like uh, take long time. I don't know, is this complex, or going here is complex? I don't know. What is backtracking? Backtracking is a problem-solving algorithmic technique that involves finding a solution incrementally, trying different options and undoing them if they lead to the dead end. Okay, so basically what you have to do is, if that's a dead end, I undo it, I delete it. That's what I do it. It is commonly used in situations where you need to explore multiple possibilities to solve a problem. Multiple possibilities, it could be anything, right? In just look at our day-to-day life coding. Just if you are going to implement a feature from an user story, there's multiple way to solve a problem, right 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 you know Not definitely in a way to speak. I do a video, that's all. Like searching for a path in a maze or solving puzzle like Sudoku. So I got that idea from there, actually, but I don't know about Sudoku. Okay, they are going to that's really sad. They are going to close this forever, and I don't know how to go down. Is there a way to go? Oh, this is all. Oh god. So it'll be hard for me to draw the Sudoku puzzle. Okay, I really don't know how Sudoku works. It's a shame, but that's the truth. Maybe like this. 5. Let's put 2, and you need to get the like 9, or I guess I'm not sure. So you try different options, different stuff. It's the same as the multiple. It's just another way of thinking to it is similar. When a dead end is reached, the algorithm backtracks to the previous decision point and explores a different path until the solution is found. All possibilities have been exhausted. Okay, that means there is a possibility that there won't be a solution, right? There might not be a solution. You just close it, and there's no solution actually. You just find every path. So, okay, that's a good question. If you don't have a solution, solution, what are the possibilities? Okay, yeah. What do you mean by possibilities? For okay, possibilities Yeah, I get it. It's not possibilities for success. It's just choices that you make, and you find out it's just a dead end, like your death. I'm just kidding. Backtracking can be defined as a general algorithmic technique that considers searching every defined as a general algorithmic technique. So there's a specific algorithmic technique. So general, yeah, that considers searching every possible combination in order to solve a computational problem. That considers searching every possible combination. Oh, I really don't understand that. Yeah, I get it. Like possible combinations. So this is a combination. So you guys remember the combination, right? There's a formula for it. Combination formula. So this one, it comes. You have these number of. I'm not sure number of combinations. Total number of objects in the set. The number of choosing object from the set. Okay, I really don't remember it, but so out of the total number of possible you choose, there is combinations. Yeah, I really don't get it. Maybe I can put some effort into it, but I don't think that's the exact thing, because yeah, it's another way to to look at a problem. That's all I think. So this has their own set of terminologies. It's just going to be something that we already know, so no one need to panic. So candidate is a potential choice. I'm just going to cut right there. So this is a candidate, probably. So going here and here, this is candidate 1, this is candidate 2. And what happened to these candidates if I find out that there is no way, and I'm going to backtrack here? So this will be candidate, I don't know. Solution is a valid and complete configuration that satisfies all problem constraints. I don't really understand this. I'm going to put this into ChatGPT. I hope my previous searches is not going to earn money with iPhone. Yeah, that's it. Nothing personal there. Okay, explain this. Sure, let's break down what solution. Solution is valid, blah, 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 blah. Valid solution, blah, blah, blah. Putting all together indicates that the solution presented is not only correct according to the problem specification, but also encompasses all necessary elements and adheres to restriction or guidelines provided. Okay, I really don't get it now. Satisfy what is? Okay, I think what is? I have prompted it for my payroll system, so yes, this is about backtracking algorithm. Okay, the configuration generated by the backtracking algorithm conforms to the problem's rules and constraints. It violates any restrictions or conditions specified. It doesn't violate any restrictions or conditions specified by the problem. Okay, just consider this as something like the problem states it should be between in 100 some constraints. I'm not sure of the constraint, how to maybe just a constraint. Let's say you can't go through this because it's smaller or something. I actually had this because to show demonstrate a I don't know, demonstrate the best possible solution. But just say you have a restriction like if you have a dark wall like this, you have to ignore this as well, something like that constraints. So solution, so valid and complete configuration satisfaction. I really don't get it still. Partial solution, a partial solution, intermediate or incomplete configuration being constructed during backtracking process. Okay, now I get it. Okay, just it's just the simple solution. So this is a solution, this is a partial solution. So even going here is a partial solution, right? That's great. That's what I think. Decision space. This decision space is set of all possible candidates or choices at each decision point. Decision space. This is decision space. This is decision space. This is decision space. Oh, this is a dead end, not a decision space. This is if you come here, it's going to be not a decision space. This is a decision space. If you choose to ignore this, you just choose not to see a way out like this. You go back to mommy. That's what you do. You just chose to ignore the fact that you can go out. You don't want to win, you just want to love this maze, and you find a deadlock. Okay, just kidding. Decision point. Okay, same like decision space. Decision point is a specific step in the algorithm where the candidate is chosen. Decision point is a specific step in algorithm where the candidate is chosen and added to the partial solution. Decision point is a specific step in the algorithm where candidate is chosen and added to the partial solution. This is just getting weirder and vague. That's what it does. It's getting weirder and vague. What's the difference between these guys? And truthfully, I really don't want to know this. This is just terminologies. I know the concept. Why make it so hard? Why do you name space? It's a space, set of all possible candidates. Okay. Set of all possible candidates at each decision point. Okay. So here's the thing. I didn't read this decision point. Should I read this from the backward? Like, I don't know. You have the solution here and then you give what solution is. Doesn't this have to be the other way around? Like, I don't know. It's like, I'm not going to say what your solution is. You're going to see what solution here is, and then you're going to read whatever the heck this is. And I'm going to tell you what decision space is, and the decision space, you need to know decision point, and to know decision point you have to read the decision point, and the partial solution somehow can get connects here. Okay, that's the only thing in the order. So I know what's a partial solution is. Why? So I need to read the decision point first. It's a specific step in algorithm where a candidate is chosen and added to the partial solution. It's a good thing that I didn't read the name of the author. I hope he never sees this. It's fine. I mean, it looks good, but why? Was in a hurry? Feasible solution. A feasible solution is a partial, complete solution that adheres to all constraints. A feasible solution is a partial or complete solution that adheres to. Okay, I just not feeling well. A decision point is a specific step in algorithm where a candidate is chosen. Okay, you choose a candidate. Like, okay, candidate is a choice, and you choose a candidate. Like, this is a candidate. Okay. Okay. Okay, solution, current solution. Okay, current solution. Okay, partial solution. I really don't get this. The partial solution is intermediate during the backtracking process. This is intermediate or incomplete configuration. So what do they mean by complete configuration? Complete means finishes. So if it is finishes, a candidate is a potential choice, or it's a potential. So whatever the choice is a candidate, and a decision point is a specific step in an algorithm where a candidate is chosen. Okay, decision point, you chose the candidate and added to the partial solution. Partial solution. So, okay, partial solution. Oh, it's a partial solution and it becomes a solution. You add it to the using the decision point. You find the candidate, and decision point, you find the candidate, and candidate is it can be added to the solution, and solution can be partial solution. Yeah. So I don't know what the hell is the candidate. So first I need to, solution is going straight, you get a solution. That's a solution. So in order to go there, it chose not to, this is a decision point. So this should be a candidate. This should be a candidate. Okay. So this is the decision point. So set of all this is called decision space. Okay. Don't look at the diagram. Look at what I'm saying. Listen properly. I have listening problems and reading problems, and I'm explaining to you. So decision space. So this is a candidate, this is a candidate, this is a solution, this is a partial solution. This becomes a solution here. Here, this is, if this stops, this is a partial solution. You backtrack and then go. So I need to delete. I hope. Okay, there is another good solution. If you, I have to okay, did I actually erase? No, you can go like this, and yes, you can go like this. I got the wall there, but yeah. So this is a solution, right? So this is a decision point. So this is a solution. This is all. Okay, I'll go with the yellow. Yes. This is also a solution. Okay. No, I'll go with the red because I don't have an idea. Okay, this is also red. I crossed the wall there. I'm in a flash. Okay, that's all. Okay, this is a decision point, and I go here and I make a decision point and I choose candidate here and I hit this. This is a partial solution. You come back to the decision point back here, and then you go like this. Okay, I can actually make a decision here again to go like this. Maybe there's a solution there. You go like this, you go like this, you make a decision here, decision in the decision point, and you choose the candidate here. If you go this is a candidate, and you end here. So this will become partial solution. You come back to this point, you choose this one, then it's still a dead end partial solution. So this is a solution and this is a partial solution. And what are the other things? Candidates. Feasible solution. A feasible solution is a partial solution or a complete solution that adheres to all constraints. Okay. So this is not actually, it doesn't adhere to the solution because I went off the wall. I could have gone like this, but I just chose to go like this. Let me do it. No, I can't do it the proper way. Then I have to correct this. Oh, I can use the eraser. like normal guy. I erase the wall as well. It's fine. It's fine. You're not going to notice, are you? Okay, okay. Connected. Fine. The constraints are given by me. Okay. Dead end. Okay, that's exactly. Finally, a term that I really know. A dead end occurs when a partial solution cannot be extended without violating the constraints. Okay. This is dead end. If I violate it, I go here and go there. But I don't violate. This is a dead end. I need to like give it a like something scary. What is scary? This one, I think this is scary. Okay, that one, I was expecting a small one. Yes. Can I fill this with color? Like red. Can this be filled with colors? What is this laser for? What the hell? Oh, really? This is a great one. This is the dead end. Backtracking involves undoing the previous decisions and returning the prior decisions, which we know. We undo this. We undo this. Why did I break the wall there? That's backtracking. Finally, I have two words that I make sense. Search space. Search space include all possible combinations of candidate and choices. Okay, candidate, you said it meant choices, and suddenly you don't want to go with the terminology. You just want to stick to choices. Okay, why? Suddenly you decided, okay, and choices. You don't want to be specific. You're afraid of making mistakes, and you made a mistake. Look at me. I have completely no idea, and I'm going to make a video on this. It's okay to make mistake, but make bigger mistakes. I don't think that makes sense, but let's go with it. Optimal solution in optimization problems. The optimal solution is the best possible solution. Optimal solutions in optimization problems. The optimal solution is the best possible solution. Okay, optimal solution. Okay, I'm just zoned out there. Optimal solution in optimization problems. The optimal solution is the best possible. Okay, I get it. Yeah, and I'm just going to read it again. Decision, feasible solution. Optimization problems, best solution. Enumeration problems, enumeration. Okay, enumeration. The problem of determining or counting the set of all solution to problem. Find all set of possible. Yes. Just feel like giving up. Yeah. I'm just going to skip to this. The best way to implement backtracking is through recursion, and all backtracking code can be summarized as per given pseudocode. Void find solution parameters. Find solution parameters. What are you going to pass there? Okay, void. Yeah, it doesn't return anything. Parameters. What parameters? Okay. If valid solution, store the solution. Return for all choice. If valid choice, apply choice. Find solution. If valid solution, store solution, return, you go out, so it's not a valid solution. Then go here, for all choice, if valid choice, apply choice, find solution. Okay, when I find it, I go to come back. Yeah, backtrack, find solution. So when I'm going to come here, like if I go like this, go like this, when exactly am I going to come out of this? Okay. Backtrack, remove choice. Maybe if I didn't find solution. Yes, it didn't. Okay, there is no didn't. Since backtracking is purely brute force, therefore in terms of time complexity it performs very poorly. It's poor performance. Generally, backtracking can be seen having below mentioned time complexities. Exponential. Wow. Really? Factorial. I don't have any idea about the factorial. These complexities are due to the fact that at each state we have multiple choices, due to which the number of paths increase and the subtrees expands rapidly. Okay. Text justification, decryption, network routing, and congestion control. Solving puzzles such as NQ problem. Creating smart robots to play board games such as chess. Oh, chess. I hope I can see in queen problem. I'll choose rat in a maze. Do you have a code? C++ code. Okay, something is better than nothing. Initializing a string direction which represent all the directions. String direction deal array to represent changes in a row. Int dr4. It's an array, right? 1 0 0 1. How do you do this in C++? DC. Okay, this is column, this is row. Maybe the first elements. It's an array which is. This doesn't make sense. This doesn't make sense at all. I don't know how this makes sense. Function to check if cell is inside the maze and unblocked. I don't know what exactly they mean, but I don't care, nigga. Okay, I just went overboard there, mate. Okay, so okay, hard. Java is there. It's better. Java is here. It's an array. Okay, I don't understand. JavaScript is here. Finally, JavaScript. So you create an array with 4 elements: 1 0 0 minus 1 0 minus 1 1 0. Function to check if cell is inside. Okay, maze and unblocked. Function is valid row column num. Return row greater than equal to 0 and column greater than equal to 0 and row less than n and column less than n and maze row column equal to 1. Okay, to get all valid paths, function find path, row column maze n answer current path. If we reach the bottom right cell of the matrix, add the current path to an answer and return. If row equal to n minus 1 and col equal to n minus 1, ounce.push current path, return. Mark the current cell as blocked. Mace row col 0. 4, let I less than 4, I plus plus plus. Find the next row based on the current row. And the DR, hurry. Okay, I think we'll continue this tomorrow. Tomorrow is good, right?